Okay, so let's talk about these electron configurations and how we're organizing electrons in our periodic table. So generally, an electron configuration describes how electrons are distributed in the various atomic orbitals. Now, before we go into specifically electron configurations, I want to take a slight sidetrack to talking about what an atomic orbital is. There was a lot more description of atomic orbitals back in chapter 3, which we did not cover, just because some of it is just not relevant to what we're doing in this course. So some of this that we're going to be talking about is coming from chapter 3, so if you'd like to read through this on your own, you're more than welcome to do that in your own textbook. But what I'm going to give you here about atomic orbitals is a nice overview so that we understand the organization that comes along with electron configurations. So, an atomic orbital is where electrons are housed in the atom. It is a three-dimensional description of the location of an electron around an atom. And we have to remember that electrons are going around our nucleus. Okay, they're three-dimensional. It's not, we used to draw our atoms like this, where it had these layers, kind of like an onion. But we have to remember that this is in 3 dimensions. So there's really, one's going this way, and I'm not good at drawing in 3D, going that way. So we have to remember that this is all 3-dimensional, and the atomic orbitals are going to help us describe the location of those electrons in 3 dimensions. So there are 4 types of atomic orbitals that we are going to utilize and talk about. That is the s orbital, the p orbital, the d orbital, and the f orbital. So we want to remember these 4 orbitals, s, p, d, and f. Those are the 4 types of atomic orbitals where we could find electrons. So, atomic orbitals are 3-dimensional shapes. And each type of orbital has a different shape, and what we're going to refer to as an orientation in space, because it's 3-dimensional. So they have to think about their orientation in a 3-dimensional world. So, to start us off, the s orbital. The s orbital only has one possible orientation in space because it looks like a sphere. So that's this image here. This is an s orbital. It is a sphere. And one s orbital holds 2 electrons. So we can fit an electron in 2 electrons in one s orbital. The p orbital has 3 possible orientations in space. Okay, so 3 possible orientations, and that's going to be in our 3 planes, our x, y, and z 3-dimensional plane. Now, p orbitals have a dumbbell shape or a figure 8 shape, so that's this image over here. P orbitals are over here, okay, and they look like dumbbells or figure 8s. And there's 3 orientations. And that is the p sub x, meaning it lies along the x-axis. So there's our x-axis, and the p orbital lies along that one. We have our y or p sub y orbital, which lies along our y-axis, and our p sub z orbital, which lies along our z-axis. So each orbital is in one dimension of our 3-dimensional space. For electrons, each p orbital holds 2 electrons. So each p orbital can hold 2 electrons. So maybe now you're seeing the pattern that with each orbital orientation, it holds 2 electrons. So overall, all three orientations of the p orbital can hold a maximum of 6 electrons. Okay. The d orbital has 5 possible orientations in space, and these ones look generally like flowers. We don't need to remember their specific names, so the specific orientation, such as, dx squared minus y squared or anything like that. We just have to remember that there are 5 orientations in space. And just like our previous orbitals, each orientation can hold 2 electrons. Can hold 2 electrons in each of these orientations, meaning in total the maximum amount of electrons is 10 electrons. So the d orbital can hold a maximum of 10 electrons because each orientation holds 2 electrons, and there are 5 orientations of the d orbitals. The f orbitals are far more complex in their shape, that you don't need to concern yourselves with them, but there would be 7 orientations of f orbitals. So of the very complex shapes that they make, there are 7 different orientations of them, meaning they can all hold a maximum of 14 electrons. Okay, so each orientation again holds 2 electrons, and because there are 7 orientations in space of the f orbitals, the maximum amount of electrons that the f orbitals can hold is 14 electrons. Okay, now in our previous chapter we talked about energy levels, electrons moving between energy levels. So our orbitals are going to be dependent on those specific energy levels. Specifically, each new energy level n comes with a new orbital group that is introduced, because as we're moving further and further away from the nucleus, we have more room. That orbit, if you can think about it that way, has a larger radius, so we can fit more and more electrons. So if this is my nucleus here, I'm going to have my first orbit, my second orbit, my third orbit. Okay, I'm drawing it in half, but because it's getting larger and larger, I can fit more and more electrons. Okay, because the electrons, they aren't changing in size, but the orbits are. They're becoming larger, so we can fit more electrons. So we see here by this energy diagram that with each new energy level, so here's n equals 1, n equals 2, and n equals 3, we start off in n equals 1 with just a 1s orbital. So the 1 here tells us that that's n, and then the s is the type of orbital. Then when we go up to n equals 2, we now have a 2s orbital as well as our 2p orbitals. Remembering that there's 3 orientations of a p orbital in space, so we have to account for all 3 of those here. And you can see those orbital shapes on the other side. Then when we go up to n equals 3, that's when we introduce our d orbitals. Okay, because now there's even more room that we can fit all 5 of those orientations in space, because we need to accommodate more electrons. And it's really important to remember that each orientation holds 2 electrons. So I'm going to write this in red. Here we're going to have 2 electrons. But then when we go up to n equals 2, I now have 2 electrons in 1, 2, 3, 4 orientations, so that would be a maximum of 8 electrons in n equals 2. Then when I go up to 3, again I have 2 electrons that are going to fit into the 3s, 3p, and then into the d, as well as there. So we have 10 electrons that can fit in the d, 6 electrons that can fit in the p, so that's a total of 16, and 2 electrons that can fit in the s. So our max here is now 18 electrons. So with each new n, I can accommodate more and more electrons because as we're moving away from the nucleus, our orbits become larger and we can fit more electrons.